Well, I'd just like to let everyone know I have the privilege of introducing the Jane Warren Award winners. If you don't know me, I'm Ellen Mantis. I'm the Director of Science at HEI, and I would first like to start with something that's near and dear to my heart, though, is the Summer Fellowship Program that I mentioned last year at annual conference. It was something we were embarking upon. It is a 10 to 12-week program. In the summer, it is for undergraduates from underrepresented backgrounds, and it was our first year last year, and we had, I think, a very successful year. We had 7 fellows who had, I hope, a very enjoyable summer experience. I think one of our fellows is here at the conference, Kai Kabilko. So if you see Kai, please say hello to him. And this year, I'm very happy to say that our program expanded a little bit. We had 81 applicants up from the previous year. 20 people volunteered to be mentors. I would like to, if any of them are here, I would really like to thank you for volunteering to do this. You'll see on the map their little hats that represent where people volunteered. We weren't able to pair a student with each of our mentors. Hopefully, in the future, we'll have more opportunity to do that, but we are very happy this year to have 9 very well qualified people to have a hopefully very enriching summer experience. So just wanted to mention our great summer fellow program that's growing and expanding, and before we start with the Jane Warren Award winners. So Jane Warren, just as if anyone is not familiar, was a person here at HEI who led the scientific activities as the Director of Science for many years. This award supports early career graduate students and postdocs to attend the conference and present. And our first person up is Jagadish Pavula, who is going to talk on maternal and placental metabolomic and epigenetic alterations associated with gestational exposure to PAHs. Jagadish?
Thank you. Hello, everyone. Today, I'll discuss about adverse pregnancy outcomes associated with polycyclic aromatic hydrocarbons, PAH in short. As you see here, it's a collaboration across multiple universities. So PAHs, these are unambiguous, mostly released in atmosphere due to incomplete combustion of organic material. A few examples of exposure include charboiled food, firewood, and also vehicle exhaust and smoke exposure. To see the associations with pregnancy outcomes, we recruited 75 pregnant individuals, collected maternal urine. We quantified 8 monohydroxy PAH metabolites, and maternal blood, cord blood. We isolated serum to measure untargeted metabolome profile, and we also collected placenta tissue using the mononuclear cells from cord blood and also fetal and maternal side of the placental tissue. We profile epigenome using the 8 PAH concentrations and features from epigenome and metabolome. We looked at associations, and using these features associated with PAHs, we then performed pathway analysis to see trends with phenotypes. So to summarize our findings, from metabolome, we observed that PAH interacted with several pathways that include metabolism of fatty acids, vitamins, carbohydrates, and energy that are linked with fetal growth, and also xenobiotics, nucleotides, and organic compounds that are linked with fetal development, lipids that are linked with fetal neurodevelopment, and glycans with transcription-related reactions. Going to epigenome, we observed several CPGs that are within the transcription start site, and here are the genes that are linked with those CPGs. And to summarize with the findings in epigenome, we observed alterations in fatty acid metabolism pathways and ferroptosis in the placental tissue. and also HSV-1 related infection pathways in pregnant individuals. And I would like to wrap up my talk by acknowledging the participants, staff included in the study, and also the funding agencies. Thank you.
Next up is Rashid Sharma, who's going to talk about the spatial variability and the acute effects of ambient air pollution and temperature on pediatric seizures and epilepsy across New York.
Thank you. I'm really happy to be here and share our work based out of New York State. So seizures and epilepsy can be highly debilitating neurologic conditions, and these particularly impact young children. And the role of air pollution and ambient temperature in causing as well as aggravating these neurologic conditions is being explored increasingly. Independently, several social stressors have also been associated with increased incidence as well as prevalence of seizures and epilepsy. But here we were interested in looking at which social stressors can bring about effect modification of the effects of environmental exposures on seizures and epilepsy. And more specifically, we were interested in spatial effect modification. So we got our data from SPARCS, which is a New York statewide data on emergency department visits for seizures and epilepsy, 16 years of data, and for seizures and epilepsy in children under 5 years of age. And each of the presenting case were assigned fine scale estimates, daily estimates of outdoor fine particulate matter pollution and minimum temperature. Specifically, we started with quantifying census tract level associations for ED visits with the environmental exposure across 7 lakh days. So starting from the day of the visit and the 6 preceding days, using a time-stratified case crossover design. And then we wanted to formally assess if there was spatial variability in these effects. So this was done using a spatial Bayesian hierarchical model. And ultimately, we wanted to identify the social stressors which could explain the spatial variability. And this was done while adjusting for spatial autocorrelation that might exist between the environmental exposures as well as the social stressors. And this is what we see. First of all, we saw spatial variability in the effects at the census tract level across each of the lag days, but the strongest effects were seen on lag day 1 for PM 2.5. And we saw that census tracts which had greater population of people who spoke English less well as recorded in the census, as well as census tracts which had higher annual murder rates. They had stronger PM 2.5 effects. For temperature, we observed the strongest effects on lag day 0, so the case day. And we observed that census tract which had greater proportion of the population that were not white had stronger effects of temperature. So thank you, and I'll see you at the poster session.
Next up is Antonio Sabarito on skyrocketing pollution, assessing the environmental fate of July 4th fireworks in New York City.
Hi, everyone. Pleasure to be here. My name is Antonio. I'm a third-year PhD at NYU, and I'd like to thank everyone who helped me in my department and put this little project together. So as we know, as most of us are environmental scientists, that pyrotechnic displays can often produce bad air quality. And so that includes PM and black carbon, but also the heavy metals that are associated that make the colorful fireworks go boom. And so there's an animation I spent way too long on, so please appreciate it. But we wanted to use our unique case study as, the Macy's 4th of July fireworks show, the largest annual fireworks show in the world, and we wanted to answer a few of our questions that we had. And so we wanted to look at the chemical composition of the 60,000 shells that were launched over 25 minutes for the Macy's fireworks parade, as well as looking at the dispersion across New York City and where those pollutants are depositing, and how long it takes for that plume to traverse over the city and the effects for nearby neighborhoods. And so to do this, we set out to do this exposure assessment. So where the red star is, that's where the fireworks were launched. We set up 4 stations where we monitored air quality in real time and looked at and used gravimetric filters to collect XRF and despeciation. We collected water samples to look at the deposition of the air samples within the water and analyzed it for heavy metals. And then used purple air and AQS modelings and model that with ArcGIS to model the plume's dispersion. And so we found that fireworks had considerable effects on both air and water quality. And so these are calibrated real-time devices that are looking at PM 2.5, well over 1,000 over the 4 sites that we collected. And then we also compared it to major cities that had 4th of July fireworks shows as well. And water quality as well. A very interesting finding increases in parts per million and parts per billion of heavy metals in the water samples that we collected in the East River. So for more data, for more speciation, please come to the poster. Thank you so much for your time.
Next up is Glenn Chuya, who's going to talk about ozone-related health impacts of hydrogen leakage.
Hi, everyone. My name is Glenn, and I'm going to be talking about the ozone-related health impacts of hydrogen leakage. I'm currently a PhD candidate, and these are my co-authors. So hydrogen leakage, hydrogen can leak from all facets of the supply chain. So it's similar to natural gas, and so when it leaks, it actually does increase surface ozone because of complex chemistry reactions that are happening. So, for example, the hydrogen actually increases peroxy radical concentrations and also methane concentrations. And in the presence of NOx, it increases surface ozone. So hydrogen has recently been under the spotlight for being an indirect greenhouse gas because it extends methane lifetime. And so, it's very similar to methane and warming impacts. But hydrogen itself is also a tropospheric ozone precursor similar to methane, as I described previously. And the costs of methane-related ozone damages have been quantified, and that's helped in the policy space. And so I was hoping to do the same in the hydrogen space for hydrogen leakage. So the key research questions are, how does hydrogen leakage affect surface ozone, and what effect does this have on human health? And so I used a chemistry climate model that's able to simulate these complex chemistry reactions that produces gridded global ozone surface ozone, and with that, I'm able to estimate the amount of respiratory-related deaths. And so what I find is that when you increase hydrogen emissions, you do increase the population mean surface ozone, and this increase in surface ozone also increases ozone-related mortality. In particular, if you see I estimated about 180 ozone attributable deaths for every teragram of hydrogen emitted, and that's compared with what we see with methane. So the conclusions here are that hydrogen leakage is an overlooked contributor to ozone concentrations, and efforts to prioritize future hydrogen use should prioritize minimizing leakage and also minimizing leakage potential. And with that, thank you.
Next up is Lucille Borzala-Lacoste, who is going to talk to us about oxidative potential of PM and its association to respiratory health endpoints in high-altitude cities in Bolivia.
Good day, everyone. Thank you, HEI, for this wonderful opportunity to be able to share this work. So this work is actually one of the last bits of work that I did with my previous institution in France, which is University of Grenoble Alps. And as you can see, this work would not have been possible without the help of many institutions around the world that collaborated with us. So just a bit of background on the work that we did. We know about the ample evidence linking PM exposure and adverse health effects. But the exact mechanisms that lead to those effects are not completely understood. In fact, many studies use mass concentration as the exposure metric, yet there's evidence saying that other characteristics of PM might be more closely linked to PM toxic responses. Hence, even with the same mass concentration, the health effects might be different. So, So one of the leading hypotheses is that the inhaled PM generates reactive oxygen species, which in turn creates cellular damage and induce oxidative stress. So in a nutshell, in conditions with abundant ROS production, such as during PM exposure, the antioxidant defenses can get overwhelmed, and this leads to various inflammatory responses. So oxidative potential analysis allows us to measure that capability of PM to generate ROS. So there's a growing number of OP studies in the world, but there is very limited information on how OP associates with health endpoints. So for this work that we conducted in 2 high-altitude cities in Bolivia, we took the opportunity to look at the chemical characteristics of PM, which allowed us to perform source apportionment using positive matrix factorization. We also looked into the oxidative potential of PM, and that allowed us to look at the contributions of these sources to OP. And we did this using a multiple linear regression model. And then finally, we were really happy to be able to obtain health data in the form of hospital visits due to pneumonia and acute respiratory infection, and that allowed us to look at the associations of these health endpoints to OP and other AQ parameters we have in this study. So to pick 2 of the main highlights of our work, we were able to see positive associations of OP, specifically measured using diethyl assay with 2 of the respiratory outcomes that I mentioned earlier, and that we are consistently seeing that role of traffic-related sources and oxidative potential. So if you're interested in this sort of work, I'll see you later at my poster session. Thank you.
And last up is Soo-Yeon Kim, who's going to talk to us about estimating global trends of air pollution attributable disease burdens, and CO2 emissions in 13,000 cities using large geospatial data sets.
Hello, everyone. My name is Soo-Yeon Kim. I'm from George Washington University. I'm greatly honored to share my research with you here today. So my research is about estimating global trends of air pollution, its disease burdens, and CO2 emissions in 13,000 cities using large geospatial data sets. And our project has 2 major research aims here. The first aim is to update global data sets of city-level air pollution and CO2 emissions using geospatial data sets. As there is very fast advances in remote sensing, measurement, and geospatial modeling methods, new global data sets about air pollution and CO2 emissions are produced at a very fast pace at the same time. So we wanted to provide timely information for better urban actions by using these data sets. So the final outputs would include PM2.5 and NO2 ozone concentrations and mortality, morbidity burdens of those pollutants, and fossil fuel CO2 emissions per capita in those 13,000 cities for this study period. And then our second aim is to compare temperature trends of city-level air pollution and CO2 emissions here. As these pollutants are primarily emitted from the same sources, so the co-benefits of mitigation efforts of either air pollution or greenhouse gases in the reduction of both should be investigated more for more effective future actions. So by using our urban estimates here, we wanted to compare those temperature trends of these 4 pollutants. So we conducted correlation analysis between those temperature trends of those 4 pollutants here. So this is a very brief summary of our research's results here. So firstly, we developed this global data sets of city-level air pollution and CO2 emissions, which will be publicly updated on our research group's websites here. And secondly, this figure is from one of our trends analysis, and this summarizes the global trends of these 4 pollutants here. To summarize these results, there has been not much progress on reducing city-level air pollution and CO2 emissions globally. However, we still found huge variations depending on global regions, so it will lead to different conclusions for different regions. And finally, we found positive correlations between temperature trends of those 4 pollutants across the majority of urban areas worldwide. So we expect it will add some indirect evidence on the co-benefits I mentioned before. So this is it, and if you're interested in my works, please stop by at the poster session. Thank you.
So I want to congratulate all the Jane Warren Award winners again, and please do go check out their posters. And now I'm going to turn it over to Dan to introduce the Rosenblith Awards.
Thanks. Gonna leave, are you? All right, so we'll switch gears here a little bit, and I'm going to talk very briefly about the Rosenblith New Investigator Award. So this is an award for junior investigators at the assistant professor level or equivalent. Applicants can be based anywhere in the world and be of any nationality. The key criterion is that their research or their proposed study is related to air pollution and health or to HEI's mission broadly. The award is named for Walter Rosenblith, who was the first chair of HEI's research committee and then was a member of our board of directors after that. So this year we have two winners that will come up and give us quick lightning talks like we've just seen. So first up we have Yosira Ornelas Van Horn from Columbia University.
Thank you so much. And I actually want to give you a shout out down because that was probably the best pronunciation of my name. For everyone else, Yoshi is completely fine. And so, first of all, thank you so much for this HEI award. I really, when I decided to apply, I really did not expect that I was going to make it far, mostly because in my head I had this idea of combining both my passions for source apportionment methods and youth engagement in Indigenous communities. So this project is titled What's in the Air? Engaging Native American Youth in the Northern Plains to Reduce Air Pollution. One of the things that you may or may not be surprised to know is that of the 576 federally recognized Indigenous communities across the United States, only 15% of them can actually even monitor or are approved to monitor their air. And so this means that not only do they not have the resources, they also don't have the capacity to actually be able to monitor their local sources of air pollution. The National Indian Tribal Air Board has done a lot of work surveying these different Indigenous communities, and of the ones they've surveyed, a lot of them have expressed that industrial wildfire and natural resources pollutions are their main areas of concern. So for this project, to the surprise of no one, my first aim is really focused on engaging Native American youth in the formation of a community air-based monitoring network, integrating both local knowledge and different phases to engage these youth. Here's a picture from last summer for one of the programs I've been involved with, where the students actually, and I was one of their mentors, we used the cubes to be able to measure volatile organic compounds because they were really worried about the potential toxics released from burning tires in their communities, as some of these, as you can imagine, a lot of these don't have proper waste disposal. And so the only way to get rid of some of this is to burn it. And so here are these youth who've only complained about this was that it was really hot. Looking back on that, it probably, right, in the middle of the summer, having to go to any of these areas, I can totally understand their concern for not wanting to sit there and monitor this air. And for AIM 2, it really focusing on this source apportionment and launching this air monitoring network. Originally, when I conceived this project, we were only going to be focusing on filter-based approaches, which we know do require a lot of upkeep and technical capacity. And so we are partnering with Missouri Breaks Research Industry, which is an American-owned community partner in the area. In talking with them, one of the things they really wanted to do, particularly for local youth engagement, was do more real-time monitors, low-cost monitors that they can actually use. And so we've integrated both Purple Air and QuantiQ to be able to give us the real-time data resolution required for this, so not having to wait so long for the filter-based monitoring the results. And so far, only about, I'm losing count, maybe it's like 2 months into this project. But big achievements so far have been getting the schools on board. We have two out of the 3 schools identified, some contracts completed, and then recently submitted 2 of my because since this does require data collection on indigenous lands, I do have to, they do require me to go through their own individual institutional review boards to be able to monitor and share results. And so I have completed those applications and hopefully moving along the process and hoping to launch the actual ERT network in the next coming months. Thank you.
There you go. Okay, thank you very much. We have our final Rosenblith winner is Rachel Nethery of Harvard University. She's approaching the stage. Yeah, I didn't see her.
Thank you. Thank you, Dan, and let me say how tremendously grateful and honored I am to be a recipient of this award. My project is called Designing Optimal Policies for Reducing Air Pollution-Related Health Inequities. And this work was really motivated by the EPA's recent statements where they've indicated that environmental justice is likely to be a priority of future policy making for them. That means that in particular, they're looking to mitigate the disproportionate pollution-related burdens that marginalized communities experience in the US. And so I thought, in theory, modern data should be able to inform us about how to optimally design policies to achieve these kinds of objectives. However, designing national environmental justice-centered policies is pretty complex. It requires accounting for different levels and sources of exposure in different areas of the country and in different population subgroups. It also requires thinking about differential susceptibility of certain groups in certain locations to the adverse health impacts of pollution exposures. Of course, in the real world, we also have to think about cost constraints. So of course, because of cost constraints, we can't reduce pollution to zero everywhere, so we have to think about where we can get the most bang for our buck in terms of intervening. So to my knowledge, at least, existing statistical methods are not well equipped to tackle all of these challenges simultaneously. So this is a gap that we're hoping to fill with this work, and we're gonna hopefully accomplish 3 aims. In aim 1, we're gonna develop methods to estimate spatially varying subgroup-specific causal exposure response curves, and we'll specifically be applying these methods in the context of nationwide Medicare data to look at the associations between PM 2.5 and health. And then in aims 2 and 3, we're gonna be developing 2 sort of separate methods that invoke these exposure response curves estimated in aim 1 to try to identify hypothetical PM 2.5 reduction policies that minimize racial ethnic group specific PM 2.5 risks. In aim 2, we're gonna be using a Monte Carlo simulation design. And in aim 3, we're gonna be developing some more formal optimal policy learning approaches. So in aim 1, we're gonna be focused on developing Bayesian causal inference methods, specifically combining Gaussian process and spatially varying coefficient modeling techniques to estimate spatially varying subgroup-specific causal exposure response curves. That's a mouthful. And then we're gonna be applying these methods to nationwide Medicare data to estimate causal exposure response curves for PM 2.5 and various health outcomes for a bunch of different racial ethnic subgroups and across all regions of the US. Then in aims 2 and 3, recall that we're going to be focused on identifying PM 2.5 reduction policies that would minimize health burdens in each of these racial ethnic groups. And in aim 2, we're going to be doing this using a Monte Carlo approach, where we're basically going to enumerate a bunch of different realistic hypothetical policies and then plug those into the exposure response curves estimated in aim 1 to then estimate the race ethnicity specific health risks of each of those policies and identify the policies that minimize them. In aim 3, we're going to be taking a little bit more of a mathematically rigorous approach, developing constrained optimization algorithms that are trying to accomplish the same task as in aim 2, but hopefully in a more computationally efficient and accurate way. The trade-off of that is that they're going to be probably a little bit less transparent and a little bit less flexible than the methods from aim 2. So we'll have 2 sort of sets of methods available for the scientific community that will hopefully get us towards this goal of being able to design environmental justice-centered policies. So as our other speaker said, I'm just getting started on this work, but down the road we hope that we'll be able to produce region and race ethnicity specific PM 2.5 causal exposure response curves. We'll be able to identify PM 2.5 reduction policies that minimize group-specific health risks, and we'll be developing new statistical methods for optimal environmental justice policy design that can hopefully be applied more broadly. Thanks.